So this is a more quantitative problem. So it says that carbon reacts with water vapor at elevated temperatures, and it gives the expression. This is carbon solid plus water gives carbon monoxide and hydrogen gas. It has a small Kc of 0.2. So when I look at this, what I'm thinking is this is a reaction that doesn't form very many products. And I'm also acutely aware of the fact that there's solid carbon there, and that carbon is not going to appear in the expression for K. So then it says, assume a reaction mixture initially contains only reactants. So that means that initially the concentration of carbon monoxide and hydrogen was 0. And then it says, what is the concentration of carbon monoxide in an equilibrium mixture with the concentration of water equals to 0.5? So I'm going to set up an ICE table and see if I can decipher what all of the equilibrium concentrations are for the different things. So I'm going to write my equation. Carbon solid plus H2O gas in equilibrium with carbon monoxide gas and H2 gas. And then I'm going to go initial, change, and equilibrium. Now, the important thing to realize is because the carbon is a solid, we're just going to ignore that column there. And then, so what do we know about initial values? We know that we have 0 carbon monoxide and 0 hydrogen to begin with, but we don't know anything about any of the other initial concentrations. So how are things going to change? Well, what's going to happen is that the concentration of the water is going to go down by some amount X. The concentration of the carbon monoxide will go up by X, and the concentration of hydrogen will go up by X. Now we know that the reaction will move towards the products here because it has to. It's impossible for it to move towards reactants because we don't have any of the products to react. So when this comes to equilibrium, we are told that the concentration of the water is 0.5, but we don't know anything about the concentration of the CO or the H2. So they're just going to be X. So I can write the equilibrium constant expression for this. It's the concentration of my products divided by the concentration of my reactants. So that's X. That doesn't need to be squared or cubed because there's only one CO. Multiplied by the concentration of H2, which is X, again only one of those, and then that's going to be over the concentration of the H2O, which we were told is 0.5. Now we know that Kc is equal to 0.2 at this temperature. So what can we say? X squared on 0.5 is equal to 0.2. So therefore X is going to be the square root of 0.2 times by 0.5, which I believe is 0.037. Let me just double check that. I shouldn't do this in my head, right? Because that's bad habit. See, I got it wrong, right? See, it's 0.032. So don't do it in your head, you just might get it wrong. There we go, 0.032. And that's it. Now, we were asked to calculate the concentration of CO, and you can see that the equilibrium concentration of CO is indeed X, so we should just finish off the question. The concentration of CO at equilibrium equals X, which equals 0.032 molar, and there's my answer. Okay, sounds good. It all looks good to me. All right. Okay, let's try another one, quite similar. 74. Get zoom in a little bit. There we go. Okay, so it says, assume the change in concentration of N2O4 is small enough to be neglected in the following problem. So what that means is that we're going to assume that the initial amount of N2O4 is approximately equal to the equilibrium amount. because the amount of N2O4 that gets converted to products is so tiny that it doesn't really change the initial amount by a lot. So let's look at part A. It says calculate the equilibrium concentration of both species in 1 liter of a solution prepared from 0.129 mole of N2O4 with chloroform as the solvent. So this is nice. We're in 1 liter, so that means that the concentration of N2O4 is 0.129 mole per liter. So we're just going to prepare this from that N2O4, and so what that means is that the initial amount of NO2 is 0, right? We only have the N2O4. So initially we've got 0.129 of that, and we've got 0 of that. So the change is always going to be towards the 0. So that's going to go up by some amount, not just x, but it's going to go up by some amount 2x, because we've got 2 of these guys, and this is going to go down by x. So when this comes to equilibrium, we'll have 0.129 minus x over that, and we'll have 2x of the NO2. Now the thing that we said is that we can approximate the equilibrium amount of the N2O4 as being the original amount. That's what we mean. So now we're going to go ahead and calculate the Kc for this. So it's products, so that's 2x all squared over reactants, which is approximately 0.129, and then that's equal to my Kc, which was 1.07 by 10 to the minus 5. So when we have a very small Kc, we'll make this approximation. So let's see what we've got now. We've got 2x squared is equal to 0.129 times 1.07 by 10 to the minus 5. 2x is equal to the square root of 0.12 times 1.07 by 10 to the minus 5. We're trying to solve for the concentration of NO2, which you can see in our ice table is 2x, okay? So that's why we're solving for 2x here. So our concentration of NO2 equals 2x, and that just equals that square root of 0.129 times 1.07 by 10 to the minus 5, and that ends up being 1.17 by 10 to the minus 3 moles per liter. Okay, I think that's right. Just make sure that we didn't make any errors there, that we used the correct value for K and all of that kind of stuff. Yeah, it looks all good to me. I'm not really seeing anything. I'm not seeing any problems here, so I'm feeling pretty happy about that. Okay, looks good. All right. Just double checking all my numbers. Looks fine to me. Okay, so the last problem is a problem that we find in section 16.4, and it's all about interrelating the equilibrium constant with the Gibbs free energy for a reaction. So there are a couple of formulas that are important here. We can say delta G equals minus RT log K. So what this means is that if I have delta G, I can convert it to a K, and if I have a K, I can convert it to a delta G. The other expression that's important is delta G equals delta H minus T delta S, and that allows us to calculate delta G's if we have delta H and delta S. Now we can often get some of these thermodynamic values by looking at the standard molar entropies and the enthalpies and Gibbs free energy of formations of our reactants and products and doing Hess's law types of calculations. So I'm just going to illustrate this for part A because it's quite a long-winded process and it would take me a long time to do all 5 of them. So what I'm going to do here is I want these I want the K at 100 degrees Celsius. Now the fact that this is not at standard 25 degrees Celsius means that I'm not going to be able to get delta G directly for this reaction from the tables. I'm going to have to calculate delta G using this formula. So what I'm going to do is I'm going to calculate the delta H by taking the sum of the standard heat of formations of my products, and then I'm going to subtract from that the sum of the delta H of formations of my reactants. And then once I've done that, I've got my delta H, and then I'm going to do the same for my change in entropy. I'm going to take the sum of the standard molar entropies of my products, and then I'm going to subtract from that the sum of the standard molar entropies of my reactants, and that'll give me that value there. And then T is going to be 373.15 Kelvin or 100 degrees Celsius. So once I've got that worked out, then I can go ahead and get my delta G using my delta H minus T delta S. Now, once I have my delta G, I'm going to plug it into my top formula there, and I'm going to get my my final answer. So let's have a look at this. I'm going to have to look in the appendix in the back of the book to find these values, and I have to be mindful of how many things of each type. So I've got so I have to look at the product. So I've got 2 ICL, so 2 times, and let me see here, 2 times 17.8 minus, and then I've got I2, that's a 0, and then I've got Cl2, that's also a 0. So this ends up being 35.6, and what's important here is I have to remember the units, 35.6 kilojoules. So that's my delta H calculated. Let me zoom out a little there. Okay, now we needed the 2 because we've got the 2 ICL. So now I'm going to go ahead and calculate my entropy change for this. So I've got 2 ICL, so 2 of those, and the value for that is 247.44. Now I'm just getting these from the appendix in the back of the book, and then I've got to subtract from that 116.14 plus 222.96, and that's for the I2 and the Cl2. And then that, once I do that, is going to give me 155.78. Now, the thing to remember here is that this is in joules. So my enthalpy change is in kilojoules, and my entropy change is in joules. So what I'm going to be wanting to do is I'm ultimately going to need my Gibbs free energy in joules. So I want to just convert my kilojoules for my enthalpy to joules. So delta G equals delta H minus T delta S. So delta H is going to be 35.6 times 10 to the 3 joules minus T, which was 373.15, delta S, which was 155.78, and I should say that's joules per Kelvin there, and then this is Kelvin. 55.78 joules per Kelvin. So the Kelvin goes, and then that was in joules. The joules goes. Oh, the joules add together. Sorry, they don't cancel. Yeah, they remain. So this is going to give me my Gibbs free energy in joules. So delta G ends up being, when I do this, negative 2.25 by 10 to the 4 joules. So now I just got to calculate my K. So what do we know? Delta G equals minus RT log K. So this means that K is going to be E to the negative delta G on RT. So that's going to be E to the negative of minus, you've got to keep your sign straight here, 2.25 by 10 to the 4 over 8.314 times, remember it was 100, 373.15, and that will be it. Now I've got a big negative delta G here. So a negative delta G indicates that we're going to have a fairly modestly large K. So this is negative 22.5 kilojoules per mole delta G. That's like moderately negative. So it's a pretty spontaneous process. And so as a result, my K ends up being 1,410 or 1.41 by 10 to the 3, which indicates that a reaction that favors products. So let's kind of have a look at what we had to do to solve. And we're just doing the A here. What I did was I knew that I was, because I was at 100 degrees Celsius, I knew that I couldn't look up just a standard Gibbs free energy for this thing. I'm going to have to calculate the Gibbs free energy at that particular temperature. So I'm going to use this guy, delta G equals delta H minus T delta S. So I go ahead and do a Hess's law type calculation to calculate the enthalpy and entropy for this reaction. And I'm just doing products minus reactants, and I'm using those standard values that are in the appendix at the back of the book. Once I've got both of those things, I put those numbers in to the expression delta G equals delta H minus T delta S, using the temperature that was given and being mindful that both my delta H and my delta S need the same units. Once I've done that, I get my delta G, and I note that it's a negative number indicating a spontaneous reaction, and then I use the relationship delta G equals minus RT log K to solve for K, with my expectation that I'm going to get a fairly big K because the delta G indicates that this is a reaction that favors the products. So once I got through all of that, I'm done. So it's a lot of work, and you're not going to get many of that type of question on a test or on the final exam. You might get one of them. So it's good to know how to do, and probably if you did all 5 of those, you would be well prepared for anything that's going to come your way.